Hello, in this video, I will go over the questions in exercise 1.0 on binomial expansion. In the first question, in order to find the order of the term, we can use the formula n choose r, a to the power of n minus r, and b minus r, where r goes from 0 to n. So in this case, the fifth term is when r equals 4. So to extract that term, we can simply write it as follows. We can do 11 choose 4, and then we have 3x to the power of 11 minus 4 times negative 5 to the power of 4. So notice that these two numbers have to add up to 11. And then if you were to put this in a calculator, you will get, well, let's do it this way. So it's possible to expand out the binomial coefficient as follows. And then 4, 2, and 8 will cancel out. And 3 and 9 will simplify to 3. So in other words, we will have this number to be 330. But we still have our 3x to the power of 7 times negative 5 to the power of 4. So by putting those through the calculator, we have these respective numbers. And then multiply all the coefficients, you should have, let me write this a bit nicely. That. So then for the following, we take the similar approach, and then we will notice that every time when they ask for the position of a term, we're actually going to need to subtract it by the, so the fifth term we actually maps to r equals 4. So in this case, the ninth term will map to r equals 8. So we always have to subtract 1. Now, using the formula, this will be 11 choose 8. But due to the symmetry, you can actually write this as 11 choose 3 as well. But I'm going to stick with this formula. So it should be, my bad, it should be 10 choose 8. And then we need 10 minus 8 of the first term and 2 of the second. And I'm going to skip all the step and just write down what it will be ultimately. So we're just gathering up basically 10 choose 8 times 3 square times 6 square to give you this coefficient. Which is a bit different than what I have here. So the answer key doesn't quite, this should have been x squared. Answer key x to the power of 7, though that is not right. Actually, even this number is incorrect. What I have is 14,580. Not sure what happened there, but let's see the next one. Here, the middle term is implying that, well, first of all, there are 7 terms here. So that means the middle term must be the fourth term. So to get the fourth term, we can apply a similar way of thinking. That means r is going to be 1 less than that. So if r is 3, then we can write 6 choose 3 as the binomial coefficient, 2 as the first term, and then we want 6, take away 3 of those. And then we have 3 of the negative 3y's. So 6 choose 3 is 20. And then 2 cubed is 8. Negative 3 all cubed is minus 27. So this should be the coefficient. Still don't know why it says y to the power of 4. It should be y cubed because it goes from y to the power of 0, y to the power of 1. So therefore this has y cubed there. So I wouldn't trust the answer key in this case. Oh, by the way, I should go back and write down x squared. This should be x8. X squared y to the power of 8. I think that's better. All right. The constant term is the one with no x's. So that's easy because we just multiply this by 9 factors. So all we have is actually this. Or if you think about it, it's basically the last term. So if we have the last term here, there are 10 terms in this question. So that means r must be 9. So if we use the formula, it will look like this. 9 choose 9. X to the power of 4 all raised to the power of 9 minus 9. Negative 3 raised to the power of 9. But then you see that this is exactly 1. This is exactly 1 as well. So you're only left with this term, which is what I wrote down ultimately here. So for constant term, it's quite straightforward. You can just extract the last term and raise it to its full power, which is 9. Again, we have last term, so you can think of this as one of the two ways again. Remember how the constant term in part D represents the last term all raised to the power of the entirety. So you can just use that. Or you can go the long about way and deduce that r is 6, plug it in the formula, but then you're going to get a bunch of ones in the front, and you are going to be left with this term once again. Now to read this, technically, this is the same as negative 1, all raised to the power of 7, 3 to the power of 7 divided by x to the power of 7. So with the negative 1 repeatedly being multiplied, because it's just an odd power, it's odd, so it stays negative. So all we got to do is to crunch out 3 to the power of 7, and then we have x to the power of 7 on the bottom. This is equivalent to this expression. So either representation will be fine. We're given the values in the fourth row of the Pascal triangle. Write down the values in the next row. So the pattern of the triangle looks like this. The side entries just get carried down, and each of the middle entries are the sum of the previous two terms on the top. So it will look like this, making sure that they're symmetrical. Hence, find the term in x of this expansion. So we know that from a Pascal triangle, the x, so actually 3x goes from 0, 3x to the power of 0, 3x to the power of 1, 3x to the power of 2, 3x to the power of 3, 3x to the power of 4. If I want only an x, we want this second term here. So therefore, the coefficient is basically 4 times 3x. But if I take one of this from the what we call the a term, right? Then the b terms will have the remaining 3 of them, remembering that these two numbers always add up to 4. So then if I put everything together, this will just be 12. Well, I shouldn't use b here. I should replace it with the proper number. So this will be 4 times 3 times negative 8, which is minus 96x. You should include the x because it says find the term in x. If it says find the coefficient, then go ahead and drop the x there. Now, another way to find this without using Pascal triangle, which I highly suggest, is thinking about which numbers do I put in here so that I will end up with something that has an x at the end. Here it's easy to see that I must have 1 from 3x, because if I have any other number, x will not be just x. It might be x squared, x cubed, x to the power 4, or maybe even just a constant. So once I choose one of these here, the remaining has to go to the other term, which simplifies to 3. And then I can take one of these numbers, any one of these, and put it in here. Okay? So actually, 4 choose 1 and 4 choose 3 are equivalent. So just put any one of these numbers here, and then you will extract the term with x in it. And that's what we're going to use in the subsequent parts. Find the x cubed term. So we have two types of terms. We have the x, we have the minus 3. You see, this is that we want 3 of these here, and then the remaining 5 to be here. Yep, so I'm going to erase that and just write down 5. I'm going to choose a smaller number here. Then this is CCS, putting things in the calculator, or again, just to show you, we can write this 8 choose 3 as a simplified form like this. 3 and 2 cancel out the 6, so we're really left with 56 on the top. But remember to have these numbers to take care of. So in any case, just put it in the calculator, and here's my answer. Now part B, don't simply just go, oh, it's x minus 3, so I want 5 of this, and then 3 of these, right? Because that's not what really what the question is asking. We want something here so that once you multiply, the x will give you x to the power 5. So that means I only want x to the power 4 coming from this expansion. So if I want 4 to come out from the combinations of these two terms, that means I must have 4 coming from x and the other 4 coming from negative 3. So the coefficient in front will be a choose 4. And then I still need to multiply by minus 2x to actually get the x to the power 5 term. So putting this together, a choose 4 is 70. Negative 3 all raised to the power of 4 should be 81, because that's 9 times 9. So we have negative 11,340 as the coefficient of x to the power 5 because of these two terms there. Okay, question 4 is an extension to question 3 part B. So again, you can't really just blindly say, oh, I want x to the power of 9, so I must have 3 of x cubed there so that it will multiply to 9. Because the remaining, so if I take 3 out of 11, I'll have 8 left, right? The problem is this number on the bottom is also going to change the overall power, the overall index. So if I expand that and just take a look of the x's, you will notice that I don't care what's on the top. Okay, I'm just looking at the power here. By index law, this is the same as x to the power of 9 divided by x to the power of 8, which gives me x to the power of 1. But that's not what I want. I want 9. So you can do a bit of guess and checking. So this doesn't work. Let me get rid of that. Maybe I can try like 5 and 3. So this will give us x to the power of 15 for the first term, and then 1 over x cubed for the second, right? With a bit of index law, there will be x to the power of 12. It's close, but it's still not quite there, right? So this is too big. Usually I would try one at a time, and it turns out that this should be 4 and 3. Because if you multiply 4 to 3, you get 12 for the first index, and then this will simply be x cubed on the bottom. So when you subtract powers, you get x to the power of 9. Now, is there another way in order to do this more effectively? Yes, there is. So first of all, if you're good with mental maths, I would just say guess and check. Because once you guess and check, you know what the answer is. Well, that has to be the combination. And then we can, finish off with the question by tossing one of these indices to be the bottom of the choosing coefficient. If you want a more generic way, well, we're trying to find a number here. So we can call this like, I don't want to call it n, but let's call it m. Okay, this is some number. And then this number is the remaining of the 11 total power here, right? So we can form a linear equation with 3m plus, now where does the 3 come from? 3 actually comes from this power here. And I'm just going to write down a little 1 on the bottom to represent this second power. So I want 3 times of some number m plus minus 1. This is where the minus 1 comes from, because this term is actually negative 3 x to the power of negative 1. So it actually contributes minus 1 of the total. So I want negative 1 times of 11 minus m, which is this power here. And together that should make 9, because I want 9 there. So if you follow this recipe, which I'll demonstrate in the later questions, we'll be able to define what m has to be in a more systematic way. So therefore, oh, I guess my answer was wrong. It's not 4 and 3, is it? 4 plus 3 actually adds up to 7. So, well, there you go. The generic way works better. It should have been 5 and then 11 minus 5, which is 6. There we go. So 15 minus 6 should be a 9. The only reason why it didn't work for the other number, because the 4 and the 3 doesn't add up to 11. So it doesn't quite work. All right, so let's get back to this here. And this is really the most challenging part, finding out the corresponding indices. So now I have 11 choose 3, which is 165, x to the power 15. Now before I ignored the minus 3 on the top, so I just put it back there. So really, we just do 165 times negative 3 all raised to the power of 6, which will be, did I forget something? Choose 3 times 3 to the power 6. Nope, looks correct on my part. So again, the answer key doesn't quite agree with what I have. And by the way, this should be a positive. But I don't see anything wrong with this. So we just take this as an answer. Now, question 5, there's a mistake here, and it's actually impossible to solve. It doesn't turn out to be a nice number, unfortunately, so we just skip that. All right, moving on to question 6. The fourth term, so I don't really like the usage of the order of the term, because technically there isn't an order. But according to the formula, we can expand 2x minus k raised to the power of 8 using this formula, right? Well, summation formula of this. So going from 0 to 8 of a choose r. Okay, so technically that will be when r equals 0, that's the first term. When r equals 2, that's the second term. So here, when we want the fourth term, we just want r to be 3. So that means we have 8 choose 3 times 2x to the power of, now n is 8 here, right? So this will be 5. That must be 3. So they're telling you that this has to equal to this answer. So we're finding what k has to be. So to go ahead and just expand the left-hand side. A choose 3 is this. And then we can put the coefficients together. So you will notice that they both equals to x to the power 5. So we can just go ahead and equate the coefficients. So therefore k must be the ratio of these two numbers, which is 216. Question 7. Okay, by inspection, you should be able to tell that out of these two terms here, in order to get a cubed b to the 6, I will need to have 3 of these terms and 3 of these terms. And then just to check 3 plus 3 is 6, well, it is. So the binomial coefficient will be 6. Choose one of these, but they're the same, so I'll just choose one of the 3's. So go ahead and just do 6 choose 3 on your calculator, or you can expand it by hand, which is 20. This will be minus b to the power 6. So therefore, now this time we only want the coefficient. So you can just say coefficient equals minus 20. So I would just strip off the coefficient right at the very end, because sometimes it's important to carry on with the powers, because it may not be what you are actually dealing with at the end. Okay, question 8 is an estimation question, but you work it like this. So you can just strip the two parts here. That's one way, but that's not exactly easy. So you can also strip it like 2 plus 0.52. Actually, for this question, it doesn't make it quite powerful, because you will actually have to expand the whole thing. So just pretend it's like a plus b. So then when you expand, you have, a cubed plus 3a squared b plus 3ab squared plus b cubed. Except I'm going to replace this with 2 and 0.52. So funny thing is, this is not an approximation, right? It says estimate, but we're not really estimating. This is actually the full answer. So this turns out to be that, and then we just round it. So not a very good way to actually answer the question. They could have done like, can you approximate 2.52 to the power of 3, maybe using two terms of the expansion. So maybe you can just use, the first two terms to get an approximation, rather than asking you to round it at the end, because this is not breaking down in a way where you can see where the accuracy of the decimal place will stop. But nonetheless, it's still an application that can be harnessed. Expand this fully, so this is like the last exercise. You can either use the Pascal triangle, or you can use the formula. I will just show you what the pattern is here. X to the power 5 plus, should do 5 choose 1, x to the power 4, negative 5 to the power of 1. So you will see that the x terms will decrease in power, and then the minus 5 is going to go up by 1, and x negative 5 to the power of 4 plus minus 5 raised to the power of 5. And they can simplify these. Five choose 2 is 10, so it should be 250. And then 5 choose 3 is also the same as 5 choose 2, which is also 20. And then there will be 125. 125 times 20 is 2500. And then we have 5 times 625, which is 3125. Oh, I got the power wrong here. X. And then 3125. Ah, this would be minus. There we go. Hence, find the term in x to the power 4 in 2x. Now, usually when they say hence, you're using the parts that comes before. So let's just write it a bit nicely. So this is what we have expanded. In order to get x to the power of 4, we actually want the x to the power of 3 term. So that once you multiply by 2x minus 1, oh, actually, no, it's more than that. Here, if you take a look at that, if I multiply something, I actually need both. I need the x to the power of 3 term and also the x squared term, because using FOIL, this will give me, my bad. I need both the x to the power of 3 and x to the power of 4 term, because if I expand this with that, this will give me x to the power of 4. And if I expand that, I also get x to the power of 4. So we don't need the whole thing. We only need 2x minus 1 times dot 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 minus 25x to the power of 4 plus 250x to the power of 3 plus dot dot dot. Okay, we don't need the rest of the term, because if we multiply 2x to any of the other term, it won't give me x to the power of 4. So here, what we have is the same as 2x times 250x cubed, and then minus 1 times negative 1. So basically, I'm multiplying this term by that, and multiplying this term by that. This will be the only combinations that give me x to the power of 4. So this will be the term in x to the power of 4. And the last question, show that they're the same. So you literally have to expand out. So again, we have 3 to the power of 4 plus 4 choose 1, 3 cube. I'm just going to write it out. So this is this expansion, right? In a different color, I'm going to do the other expansion. Oh, I did something wrong here. Okay, so if you actually compare the terms, they're very much alike. So we compare these ones here, they're actually exactly the same. Except for the binomial coefficient. But I've told you before that 4 choose 1 is technically the same as 4 choose 3. Okay, they're both equals to 4. And of course, 4 choose 2 is 4 choose 2. Yeah. So even though these two numbers look a bit different, right, they're actually the same. So therefore, they're equal. So part B asks, would this always be the same? Well, actually, with a simple proof, yes, from what we have seen before, because of symmetry. But algebraically, what we can do is as follows. Actually, there is an exception. This only works if it is even power. So you can take away a negative or factor out a negative. minus, I'm horrible at this. If you take away negative, I can switch the order of term inside. So technically this is negative 1 raised to the power of n ax plus, why did they say this? B minus ax is, hold on a minute. Oh, sorry, okay, they are actually not the same. There's no reason to prove it because it doesn't work. If you show this for 3, so if you try, no, it's not always the same. So a counter proof will be using the same equations as before. We test this. We want to see if these are the same. And if you expand it this time, it won't be, because we have 3 cubed plus 3 choose 1. Okay, I'm just going to write out. Okay, that's the left-hand side. And for the right-hand side, okay, so if you take a look at the terms here, they kind of look like they're the same. And they are. Why? They shouldn't be. They should not be the same. This is really odd. Let me check. 3 choose 1, 3 choose 2, 3 choose 3. Oh, you know what? No, there's a mistake in the book as well too. Yes, this is already the same because this is just switching A plus B and B plus A. Of course, they're always the same. So yeah, I think there's a mistake in the book as well too. I think they meant to actually do this. I think they meant to say this. It's B minus AX the same as AX minus B, I think. Because, yeah, I think that's what they meant. Actually, I think the whole question is erroneous. I think it was supposed to prove 3 minus 2x, does it equal to 2x minus 3? Yeah. In that case, they are, because this is even power, so it will cancel out. But then you will see that this will not equal to that. Okay, I think that was the intention of the question. Well, anyway, for the question that was stated here, yes, they are the same actually. So given that these are the same, because basically it's just changing A and B's order. Yes, they are the same. Yes, they do. All right, hope you learned something, and see you in my next video.